human population dynamics. This is going to be lecture number 1, and this is slides 1 through approximately 20. So as we start human population dynamics and we look at how the population has changed in the world since humans have been on Earth, there's been huge changes, especially in the last 150 to 200 years. As you look at the future, the projected population is meant to increase. This is a very conservative estimate. Most estimates actually go up to about 10.5 billion between 2006 and 2050. The debate over whether population growth is healthy or unhealthy depends on your personal moral beliefs, your religion, your race, your culture. It's incredibly controversial. It's one of the big issues that we'll be coming back to again and again in this class. Most of the population growth right now occurs in developing countries. A developing country is something like China and India, where their standard of living is still increasing, where their hygiene and medicine, technology, all of that is still increasing. A developed country is one like the USA, most of Western Europe, England, France, Spain, all of those are considered developed countries. Their growth rate has slowed and is stable right now. So again, it goes back to some people think that there's too many people, that the world is overpopulated. Some people think that we can put billions of more people on Earth due to technology advances. This is a debate, again, that takes your personal beliefs into account. What should be considered when you're thinking about this debate is the standard of living. What standard of living is acceptable to you and acceptable for your fellow human beings? The other thing to take into account is the resources, the natural resources. So the standard of living would impact, hygiene, medicine, how much space does each person have to call their own, stuff like that. The natural resources is something that, yes, with technology we can put a whole bunch more people on the planet, but would there be giraffes still? Would there be whales still? Would there be all the natural resources, the biodiversity that we've come to count on? And how would the planet have changed over time with those billions of more people? So the two big factors that have impacted human population growth is the expansion of agriculture and industry. With the increase in farming and the improvements in farming and agriculture, we've gone from small either subsistence farming, where people are farming their own personal plot, to small farms where people are farming for local community, to massive, incredible farms whose size is on a scale it's unheard of, that ship their produce or their animals, their meat, whatever it is that they're raising, off even out of the country. So that has made a huge difference in able to expand, because now food is much more readily available than it was 100 or 200 years ago. The same is true for industry. Our industrial production has increased dramatically, especially in developed countries, and again that has added to an expansive population growth. So this is cause number 1, and then cause number 2 is the improvements in hygiene and medicine. So we can cure a lot of diseases that we weren't able to cure 100 years ago. We know more to wash our hands after going to the bathroom or blowing our nose or whatever, and improvements in all of those have led to lower death rates, to longer lifespans, and that has increased the human population. Some examples of that: 2006, developed countries were about 0.1% per year. Developing countries 15 times faster than that at 1.5% per year. The carrying capacity of Earth. Carrying capacity is a term that we're going to be coming back to again and again, both for humans and for every other species. Carrying capacity should be one of your vocab terms. Make sure that you're comfortable with this and know it really well. It's the number of individuals in a population that area can support. Okay, so that area can support. Hopefully you can read my scratching. In a population that the area can support. And so every area and every species has a different carrying capacity. So we could look at the carrying capacity just of the U.S. We could look at the carrying capacity of the entire world for human beings. We could look at the carrying capacity of the U.S. for squirrels, or whatever the case may be. So we're going to be applying carrying capacity as a concept to humans in this unit. So the whole world, like I said, that 10.5 billion is that number projected by 2050. But most of that development, 97%, is going to be happening in developing countries where the people are really poor. So that goes back to that standard of living. Is it worth having billions or more, thousands or more people, whatever the case may be, in an area alive on the world if their standard of living is in acute poverty, where they're not getting good medical care, where they don't have a lot of materials or space to call their own? Is that worth it? The question that I want you guys to keep in mind throughout this entire unit is the core question, the core controversial question of this unit. What is the optimum sustainable population of the Earth based on the cultural carrying capacity? And how does this make a huge impact on your answer? The UN has given a world projection for population looking at number of children per woman. And so you can see how big of a difference it makes in the birth rate for our overall population. So if women only have 1.5 children on average, our population is only going to be around 7.2. But if women go all the way up to 2.5 children per woman, our population expands much more rapidly and goes up to a 10.6 billion by 2050. So this is where we are approximately right now, and this is how things could go depending on different averages and how you look at stuff. So this could be applied to different countries. In the U.S., we tend to have fewer children per woman. In some of the developing countries, they still have a lot of children per woman, and we'll talk about the reasons for that a little bit later. Okay, so this is one of the key formulas that you guys should be familiar with. It's really incredibly self-explanatory. Don't make this too hard. All of the stuff coming in minus all of the stuff going out is all that we're looking at here. So the population will change by everybody born and everybody moving in minus everybody that dies and everybody that left. That simple. Don't make it any more complicated than you have to. When they refer to crude birth rate and crude death rates, it's based on the number per 1,000 people. So if they give you a crude death rate of 7, that's 7 people out of 1,000 would die, and that's just a little bit easier numbers to handle and to deal with. So these are kind of like the units that they're using for these numbers, most commonly accepted. The speed that a population grows or declines looks at age structure. So age structure is something that's really important to a population. This is one of those key factors that impacts the population, is its age structure. If a lot of the people are young, are not reproducing, then your population is not going to grow very quickly. If a lot of your age structure in that population are reproductive age, are capable and are reproducing, your population is going to go pretty fast. And then your population will probably decline if most of your population is considered post-reproductive age and are too old to reproduce, are past that reproductive stance. So the age structure of your population determines its growth or decline. So we can't just keep going forever and ever and ever. We have to stop somewhere. So there's a couple of terms we use for that. The intrinsic rate of increase, or R, intrinsic rate of increase, is what would happen if we just kept growing, if resources were not limited. Resources not limited, if we did not have a carrying capacity. If nothing was stopping us, we would keep growing indefinitely. And then the carrying capacity, K, is the maximum population like I talked about already. What can sustain without degrading the habitat. This is a key right here, without messing up the regular balance. So that's, again, gets controversial for us because some people argue that we have far exceeded our carrying capacity because we have degraded our habitat. So not only have we passed the maximum population, but we need to back off and make less people on the planet so we can get back to the habitat. And that's a very extreme thought at this point for a lot of people. Okay, so this growth curve shows the same thing. And it applies though, so you've got your carrying capacity right here. That's your K value. So this is the population and what can hold. And this graph can be applied to any population: humans, animals, plants, bacteria, protists, whatever population you want to apply it to. These factors all are the same. So what happens in a regular population curve is that initially, for whatever area you're looking at, there's exponential growth. We have plenty of resources, we have plenty of potential, there's all kinds of stuff happening, made available to us, we have space, we have food, we have all the stuff we need. So we keep reproducing. This is great, life is good. So this is that J curve right here. J curve, you see the J, okay? J curve right here. And then at some point we're going to hit our carrying capacity, and what happens here is that now we're starting to have limiting resources. We're running out of space, we're running out of food, we're running out of some other resource that we need to keep growing. So the population will keep growing until they hit that problem, and then something happens to kill off some of the population. So there's not enough food and a whole bunch of individuals starve. There is a catastrophe due to loss of space or disease or anything like that. So you see this S curve start to take effect as limiting resources and resistance pile on and cause decreases below the carrying capacity, which then the population adjusts because now, look, I've got more resources available, now I'm going to go back up a little bit, but then I hit this next problem, I'm out of resources, I go back down. And so you see a fluctuation called an S curve, sideways S curve right here, in the population around the carrying capacity. So a population doesn't necessarily reach and remain exactly at the carrying capacity. They will normally fluctuate around it. Okay, so I just discussed this. As you hit the population, you have this initial overshoot where you keep going, but then there's a big problem, and then the next overshoots are not as bad. You see this S curve. It's not always a pretty nicely shaped S. It kind of depends on what's going on and what population you have, but it's somewhere around the carrying capacity. Okay, so looking at what happens with populations, once they hit that carrying capacity, they have a couple options. They can maintain that S shape and just keep kind of hanging out there and doing what they're doing, but they can actually increase the carrying capacity by a couple different ways, by adapting and changing to fit the environment. So migration is a big one. We have done that. This is a big thing that you don't really think about it too much, but humans have migrated. They've spread out, they've explored new areas, they've adapted to new climates. We started out, near coasts, we started out in caves, we started out hunting, gathering, whatever. Now we've moved to deserts, now we've moved to a lot more inhospitable environments because we have the technology to do that. So we've migrated and moved to other areas, adapted to other environments. We've used our technology, we've used our culture, we've used our sociability, our use of tools, our ability to learn, all to extend our to increase our carrying capacity. So this is something that's definitely holding true for humans. Population density is defined as the number of individuals in a population found in a particular area or volume. It's exactly what it sounds like. Again, density is mass divided by volume. How many individuals in that area? the population density affects a population growth because the more animals or people or whatever you have in an area, the more you have biotic factors like disease, the more you have fewer resources per individual. So as density, let me go back, I'm sorry. As density increases, you have population at times will decrease after a time to catch up because of disease, because of fewer resources, less space, stuff like that. Less space. Okay, so population density can affect itself, can affect the population growth. Some factors that control population are not affected by the density. That would be like something like the weather, a natural disaster, a hurricane or a tornado or something like that can impact a population, but doesn't have anything to do with how many people are there. Indirectly, it may, if you have a weather pattern hitting a high density area, then you're going to have a much higher death rate, in which case your population will decline more. But weather hits indeterminately, we can't control that, so it's not determined by the population density. Okay, backing up a little bit to reproductive patterns, you've got two different types of animals. You've got opportunists and you've got competitors, two different types. And this is in the way that they live their lives, in the way that they approach population, and that therefore controls how their population is affected by both population density factors and non-population density factors. So if you look at our carrying capacity, you've got your R species, which are your opportunists. These are R species right here. They have a lot of babies. They have not a lot of parental care. These are the smaller critters. They tend to be invertebrates. They tend to be, their population will change a lot. So they tend to be a lot of J growth and then drop way off, and then more J growth and drop way off. So they tend to be well under their carrying capacity, and they don't usually end up with that S shape. They usually stay with the J shape. Okay? The K-selected species are the competitors. K-selected species are competitors. So these are the fewer offspring. We are a K-selected species. We tend to have relatively few offspring. We put a lot of parental care into each one. Our babies can't just go from the time they were born. They need help. And so we tend to be more like that S shape around that carrying capacity curve. Looking at that in a little more depth, as I said, the opportunists are the R-selected, the K-selected are the competitors. So let's look at each one individually. So if we look at an R-selected species, a couple examples, a cockroach, a dandelion. You can go further, you can say a fish, any number of invertebrates, bacteria, all of those. Lots of offspring. They don't put a lot of time into parental care or protection. They reproduce when they're young. And they have a high death rate. So this is something that you may have 1 million babies, you may lay 1 million eggs, and you may have 5 reach adulthood out of 1 million. And that's just one strategy of the two strategies. You're not putting much time into it, so it doesn't matter that you have such a high death rate, because everybody else is having 1 million eggs too. So you have that many babies because you know that you're going to have a high death rate. Tends to be small-bodied, invertebrates, stuff like that. Some more basic vertebrates like fish. Adapted to unstable climates. They're not living long. They're reproducing early, so they don't have to have something that's super stable. If some crazy weather thing comes in, the population recovers pretty fast because the next individual to have babies has 1 million babies, and they repopulate and continue to grow. So they have a high population growth rate. Like I said, this is that J curve most of the time. and it fluctuates a lot. So you have this J curve, it drops way down, like I said last time, and then you have another J curve, and then it drops way down. So there's a lot of fluctuation. A generalist niche means that they're not well adapted to something particular. They can go, a large range of options. For where they live. Low ability to compete. They don't have a lot of, if something else comes in and eats the same food and lives in the same place, they don't really have the resources or defense mechanisms to win the fight. They're just going to get out-competed. They're going to disappear. And then the last one is early successional. So these are ones that come in right after a major catastrophe. They're the first ones to settle and take advantage of an area. And then they kind of get replaced by other stuff. A K-selected species is one like us. So these are the vertebrates. These are the long-term, long lifespan, fewer offspring. We put a lot of time into care into each offspring. So we'll only have small amounts, which relatively somewhere between 1 and maybe 20 offspring, but of those, like 97%, 98%, 99% will all reach adulthood. Okay, so there's a much higher survival rate. The animals tend to be larger, they tend to be more complex, larger brains, able to use tools, able to think more complex behavior. They need a much more stable climate if they're not as able to adapt as the smaller critters. They have a slower growth rate. If they're reproducing later and they're having fewer offspring, they're not going to grow as fast. Okay, it just makes sense. Population size stays fairly stable, so you've got this carrying capacity, you've got a small fluctuation around your carrying capacity most of the time. You've not got a lot of stuff. And then they're really able to compete with other critters, able to hold their own really well. Oh, I don't know what I just did. I apologize.